I'm going to describe the phase behavior that can occur when we have two components that are only partially miscible in the liquid phase with each other. So the idea is if we had a pure component A, the green circles, and a pure component B, the blue circles, and we mix them together, we'd actually get two distinct phases. One phase we'll call the alpha phase, and those is mostly component A, mostly green. The other phase, the beta phase, is mostly component B. And so what we're interested in is what's the behavior as a function of the relative amounts of A and B that we mix together and as a function of temperature. And one of the things that we want to keep in mind when we look at these phase diagrams is the phase rule, which says the number of degrees of freedom is 2 plus the number of components minus the number of phases. So we're talking about a binary system, so 4 minus the number of phases. And the phase diagram that we're going to look at is one where we fix the pressure. So let's look at that phase diagram. So in this phase diagram, we're plotting temperature on the y-axis and the mole fraction of B on the x-axis, and then the bar graph on the right shows how much we have of each phase. In this case, we're starting where we have the alpha liquid, namely we have both components, but they're miscible in this concentration range at this temperature. So we only have one phase, and therefore for relative amounts, moles, we have 1 mole of the alpha phase. If I were to add additional B to the system, increase the mole fraction, let's move to here. Now this point in this white region, this point center, corresponds to two distinct phases. The alpha phase has a mole fraction of component B of 0.011, and the beta phase has a mole fraction of B of 0.93. And so the relative amounts of each of these phases we can calculate from the diagram using the lever rule. And if I increase the mole fraction, move to the right, then we have more of the beta phase and less of the alpha phase. And over here we have one phase now, and this is a single phase that has both components. So the other interesting behavior is as we raise the temperature. So let's look at this mole fraction and raise the temperature. So now we're on this line at about 77 degrees centigrade. Now we have all three phases present. Well, if we look at that Gibbs phase rule that we just mentioned, where for a binary system, number of degrees of freedom was 4 minus the number of phases. So we have 3 phases. That says we have 1 degree of freedom. And what we've said is the pressure. So remember, this diagram is at 1 pressure. If we change the pressure, the diagram is going to change. And so we've set the pressure. We have no degrees of freedom, which means there's only one temperature where we can have all 3 phases present. Now, the amounts of each phase is not determined by the lever rule. As I add heat to this system, you'll notice, of course, we have more vapor and less of each of the liquids, but we stay on this same temperature even though we're adding heat. If I add enough heat, the beta phase disappears. Now I have an alpha liquid in equilibrium with the vapor. This behaves the way we normally are used to a binary system in which liquids are completely miscible. We have liquid and vapor in equilibrium. The relative amounts can be determined from the diagram by the lever rule. And then if I move the mole fraction over to here, then we have beta liquid in equilibrium with vapor, and again the relative amounts determined by the lever rule. If I change the mole fraction, I change the relative amounts of vapor and liquid, And of course, for the same amount of heat added, the temperature is changing because it takes energy and heat to vaporize. So this is just a brief overview of a temperature composition phase diagram for a binary system in which liquids have limited miscibility.